Hello everyone, myself Dr.I.Baranilingesan, Assistant Professor, Department of EEE, KPRIET Institute of Engineering and Technology, Coimbatore. Today we are going to discuss about the topic semiconductor devices. In these semiconductor devices, we are going to discuss about construction, operation and characteristics of the PN junction diode and Zener diode. Let's discuss what is PN junction diode, how the PN junction diodes are made up of the semiconductor material. Semiconductor devices are electronic devices with the conductivity between a good conductor and an insulator. The semiconducting materials of the semiconductor devices are silicon, germanium, or gallium arsenide, which can be used for rectifiers, oscillators, light emitters, amplifier, and photometers. Even we can also use some other devices. So these are all the some applications of semiconducting materials. The semiconducting material devices are classified into category of two-terminal semiconductor devices and three-terminal semiconductor devices. Let us discuss what are the two semiconductor devices. Diode, Schottky diode, light emitting diode, diode, Zener diode, photodiode, or otherwise we can call it as a phototransistor, pin diode, laser diode, tunnel diode, photocell, solar cell, gun cell, and even we have some other cells also there. So these are all the two terminal devices. This diagram shows the various types of two terminal diodes. Let us discuss about three terminal semiconductor devices. Namely, we can say it as the bipolar transistor, field effect transistor, MOSFET, insulated gate bipolar transistor. Simply, we can say it as the IGBT, or we can say it as a thyristor or silicon controlled rectifier, triode, unijunction transistor. These are called the three terminal semiconductor devices. PN junction diode. Let us discuss the PN junction diode first, then we can go for the Zener diode. The PN junction diode is a combination of P type of semiconducting material and N type of semiconducting material that is shown in the figure A. You can see here the P type of semiconducting material as well as N type of semiconducting material. In between, we are having the depletion region. Let us discuss how this depletion region forms and all. And figure B shows the symbol of the PN junction diode. It consists of two terminals. One is the anode part and another one is the cathode part. And figure C shows the practical representation of the PN junction diode. A stripe mark indicates the terminal called cathode. Based on the cathode only, we are just going to find out the PN junction diode anode part and cathode part. As we know that PN junction has a two terminals called electrodes, P region and N region. N and P regions are connected to the external terminals through ohmic contact. A plane dividing N region and P region is called the junction. The diagram shows the electrode 1 and 2, that is going to be a anode part and cathode part. In between of P and junction, there is one junction is called depletion region. This diagram shows the movement of the holes from P region and electrons from the N region. Let us see this diagram. In this diagram, it consists of N region, it consists of P region. In between here, we are having the PN junction layer. The region is formed by the immobile ions is called the depletion region or depletion layer or space charge region. Come to this diagram. Here we have a P doped semiconducting material. Here we have a N doped semiconducting material. In P doped semiconducting material, the majority carriers are the holes and the minority carriers are the electrons. Where in case of N doped region, the majority carriers are the electrons and minority carriers are the holes. Now, the thing is that here we are having the majority holes, and in N region, here we are having the majorities are electrons. Now, these opposite poles are attracted to each other, so that holes and electrons recombination pair occurs in this region is called the space charge region, or we can say it as the depletion region. And it will become the immobile, and it will try to block the flow of electron from the N region and flow of holes from the P region. So there won't be a movement of electron as well as the hole. Even though after this depletion region forms, there will be a electrons are formed in the depletion region of P side, and N side there will be a holes will be formed here. Now, there is no movement of electron as well as the hole, it will become the barrier. Now the thing is that we want to move the electrons hole combination, and the charge carriers has to be moved from p region to n region, n region, p region. This has to be achieved with help of the biasing technique. The biasing techniques are called forward biasing and reverse biasing technique. So this is a diagram of the forward biasing. This is the forward biasing. It consists of the p region as well as the n region. The P region and regions are nothing but semiconducting material. As we know that the majority carriers are present in the P regions are holes and minority carriers are electrons. Where in case of N region, the majority carriers are the electrons and minority carriers are the holes. Now the thing is that here, if we are using a silicon as a semiconducting material, there will be a barrier potential voltage zero point 0.7. Or else, if you are using a germanium, there will be a barrier potential 0.3 volt. Here we are providing the forward biasing voltage. This forward biasing voltage should be greater than that of the barrier potential voltage, so that only the electrons holes movement will be happens in this circuit. Otherwise, it won't move the electrons. Now the thing is that we are going to gradually increase the external power supply, so that only the electron hole recombination pairs occurs. Now, coming to the point, the P type of semiconducting materials is connected to the positive of the power supply, and N type of semiconducting material is connected to the negative of the power supply. When we are providing external power supply to the circuit, already know that if you are using a semiconducting material as a silicon, there will be a barrier potential voltage zero point 0.7. When this forward bias voltage greater than that of zero point 0.7 voltage, so that only the movement of the electron hole pair can occur. That is mentioned in this slide. P region is connected to the positive of the terminal of the DC source, and N region connected to negative of the power supply. The free electrons from N sides are pushed towards the P side, and holes from the P region moves towards the N region. Holes converts the negative ion into neutral ions. The width of the depletion region reduces, the barrier potential also reduces. At a particular value of the V, the depletion region will get collapses. When the applied voltage is greater than the barrier potential, the depletion region will be disappears and the diode starts to conducting. The large number of majority carrier crossing the junction, a current is called the forward current. The direction of the forward current is from anode to cathode. Now, this is the characteristics plot of the PN junction diode. Here, the mentioned as the VF is equal to zero point 0.7 volt. As we know, the silicon has a barrier potential voltage of zero point 0.7 volt. When we are providing external power supply greater than that of zero point 0.7 volt, the diode starts to conducting. This is the conduction part. And this is your voltage part, and this is your current part. So, this diagram represents the forward bias voltage. Now, we are going to discuss about the reverse biasing of PN junction diode. Let us see the same diagram we are having here. The thing is that here we are going to give the reverse polarity to the PN junction layer. Here we have a P type of semiconducting material. The P type of semiconducting material connected to the negative of the power supply. The N type of semiconducting material connected to the positive of the power supply. Here we have the negative of the power supply. In this P region, we are having majority carriers are holes. In this N region, majority carriers are electrons. Now the thing is that here we have a positive power supply connected to the N layer and the negative power supply connected to the P layer. Now the thing is that here we have a positive terminal, here we have electrons. So opposite poles are attracted by each other. So the majority of the electrons are attracted by the positive of the terminal. And in these holes, here we have a holes are considered generally considered as a positive terminal. Now the thing is the external power supply, negative of the power supply connected to the positive of P type of semiconducting material. So it starts to attract the holes in the P region. All will be attracted by the negative of the power supply. So the remaining minority carriers are present in the P regions are called electrons, and the N region, the remaining minority carriers are present in the N regions are called the holes. Now, when we are gradually increasing the reverse bias voltage, at certain point, the reverse bias voltage will be very high. We know that in this electrons will move as soon as possible because it has a less weight when we are comparing to the holes. holds as the mass, so it has some weight. So this weight will be very much higher than that of the electron. Now the thing is that here the electrons higher the holes starts to cross the junction in a very fast manner, so that at the time the depletion layer will get breakdown. This is called the avalanche breakdown. Now the thing is that the P, as we know, as we discussed in the previous slide, the P region is connected to the negative terminal, and the N region is connected to the positive terminal of the source. The holes are attracted to the negative terminal of the supply, and electrons get attracted towards the positive of the terminal of the supply. The width of the depletion region increases, thereby increasing the barrier potential. The reverse saturation current flows due to minority charge carrier. Here you can see this VA characteristics plot of the reverse biasing mode of operation. Here we have the voltage, here we have in the current. Now you can see here there will be a plot. This plot shows the reverse leakaging current, that is called reverse saturation current. However, if the reverse voltage gets too large, a phenomenon known as the diode breakdown occurs. The reverse voltage at which the junction breakdown is called breakdown voltage. Next important parameters, maximum forward current. It is the highest instantaneous current under forward bias condition that can flow through the junction. Peak inverse voltage. Sometimes this kind of question can be asked in a part A question. It is the maximum reverse voltage that can be applied to the junction if the voltage across the junction exceeds under reverse bias condition. This junction gets damaged. Maximum power rating. It is the maximum power that can be dissipated at the junction without damaging the junction. So this is the combined form of VA characteristics of the PN junction diode. Next, we'll discuss about the Zener diode.